Okay, dear students, so now we're moving to the topic which is known as energy level diagram. So what are we going to do? And this is we have the expression for the total energy, which is 13.6 divided by n square EV. The unit is electron volt, it is not joule. This is the total energy, and in the case of hydrogen, we are going to find the energies of each level like E1, E2, E3, E4, E5, and then we are going to learn about the various transitions and each and everything. So this topic is very important. But before we move into the energy level diagram, there is another thing. I know that you are going to confuse these two things together. So that is why let us go for that first. So we have the expression for the radius of the orbit. Also, let us imagine how Bohr might have imagined the atom of hydrogen. How does it look like? First of all, the nucleus is having a very small size here. We are going to learn about the radius of a nucleus in upcoming videos. So at that time we will see. So now we are concerned with the radius of orbits and the radius of atom. So the expression for the radius is 0.53 n square angstrom. So this is R1. Let us say R1 in the case of hydrogen will be 53 angstrom. What about the R2? Now I'm going to substitute the value of n as 2 here. So it will become 4 times R1. Now, I want to find the radius of the third orbit. This is second, this is third. Where is the radius of the third orbit? I'm going to plug in this value as 3. It will become 9 times the first radii. What about the fourth orbit? 16 times the first radii. And what about the fifth orbit? It will become 25 times the first radii. It means that according to the imagination of Bohr in 1913, he imagined the atom to be looking somewhat like this. He said that the nucleus is very small, the first radii is very small, and the second radii should be 4 times the first, and this will be the 9 times, and this is 16 times, and this becomes even bigger, like 25 times bigger than that. So this is how the atom should actually be looking like. Okay, it's not about the energies now, it is literally about the radius. It is literally about the radius of the orbits. How is the atom looking like? Clear? So this is how the atom looks like. Now we are going into our actual topic, which was energy level diagram, and we want to find the energies here. So I am just plugging the value of n1 as n as 1, 2, and 3. So the first energy is coming out to be 13.6 eV. So when electron is moving in the first orbit here, the total energy of electron is negative 13.6. What about the second energy? Second energy will be n is equal to 2. We plug that value here and we are getting the value of 3.4 eV. I remember it. You can plug in the value as n is equal to 2, you would be getting this value. Similarly, the energy of electron in third shell here, this is third shell. So the energy is coming out to be 1.51 eV. What about the energy in the fourth shell? It is 0.54 eV. What about the energy in the fifth shell? I don't remember that. It's almost, I think, 37 electron volt. I don't remember. Just plug in the value and see for yourself if this value that I have written is correct. These are the various energies of the electrons. So we know that this is n is equal to 4, this is n is equal to 5, and there is a lot of distance between these two shells because the radius is definitely becoming bigger. It was 16 times R1, now it is 25 times R1. So definitely this electron is at a farther distance from the nucleus. This electron is at a nearer distance, but you can clearly see that the energy level difference between the shell 5 and the shell 4 is not much. So the energy of electron in fifth shell and the energy of electron in the fourth shell is not that very different, almost same. It's very easy for the electron to jump from 5 to 4 or 4 to back again 5. It's very easy for electron to keep shifting. This happens in the case of conductors. Like you talk about iron, you talk about those things. The electrons at the outer edges, outer shells, it's very easy for them to flow. So when they keep on flowing like this, they create a conductive atmosphere. But if you talk about the electron in shell number 1 and shell number 2, you can clearly see the distance is not that very big, but the gap in energy is whooping. It's big. 10 electron volt. It's that big. So this energy gap is very big. It is not visible in this diagram. So that is why we are interested in creating the energy level diagram, in which the diagram is created, the shells are created, they are arranged according to the energy. Let us do that now. So I'm getting rid of everything. Let us move to the next diagram. So the next diagram is this. So what is happening, you see, this is n is equal to 1. We are just taking it as n is equal to 1. This is n is equal to 2. This is n is equal to 3, 4, 5, 6, and this is 7. So this energy level, they are becoming very, very near to each other. And after a certain time, you will find that this energy level is the highest one. Because like, what is the energy for the fifth shell I have written? 0.37, I think. 0.37 electron volt. So this energy is becoming zero very soon. It's very near to zero. This energy level is negative 13.6. This is negative 3.4, negative 1.51. This is negative 0.84 EV, like that. Clear? So this energy is becoming zero very soon. And now it is very clear that this gap is the longest of all. The biggest of all gap is this. Okay. Now, what are these lines shown here? Again, these are very important for us. Listen to this. This series is given a name which is called Lyman series. And what is happening in this? The electrons are jumping into n is equal to 1, and they're jumping from all the various shells. It could be jumping from n is equal to 2, could be jumping from 3, 4, 5, 7, or infinity. So electron could be coming from any distance, but they are jumping into the first shell. Got it? So this is known as Lyman series. Now when the electron is jumping into n is equal to 2, but it is coming from any various n, it could be 3, 4, 5, 6, 7, it could be anything, but it is jumping into 2. These series are called Balmer series. This series is given a name Paschen series, bracket series. If you're going into 5, this is known as whatever you call it, P fund or whatever. So this is P fund series, and then there is another series in 6. I don't remember the name. So there is another name here. So these various names are given to all of these series. These are the transitions which electron is making. Electron is jumping from higher energy level to lower energy level by emitting some energy. So here some energy is emitted. Clear? So this is what is the energy level diagram in the case of hydrogen atom, which is very popular. But in the case of IB physics, we do learn about many other elements. We do learn about the mercury and all. But don't worry, that will be given to you in the question itself. So you need not to remember anything. It could be a similar diagram. The different energy will be given in the case of mercury. You have to find the gap in the energy. That's it, nothing more. So what else I can show you here? So there is another piece of information which I have seen IB people have asked you in paper 1. So when the Lyman series is occurring in the case of hydrogen, the energy which is emitted is ultraviolet. So the range of the wavelength here from this to the electron which is jumping from infinity, there is a range of wavelength and frequency. So that range belongs to UV range, ultraviolet. So this is ultraviolet. In the Balmer series, when this is emitting some energy, it is emitting energy in the visible range. Visible range means that they are emitting various colors. This is what is happening in your LEDs. So you have LED, like the energy, the transitions are taking place, and you can create any color out of it. This is what is happening in your LED TV. These transitions are taking place at that time, and they create whatever color they want. This is visible light. In the case of Paston series, you are emitting infrared. And in the case of bracket and all, you are emitting infrared later on. For everything, then there is infrared radiation, which is emitted because the wavelength becomes very big, and so they are infrared. Okay, so this piece of information is also important for you. They have asked this question in paper one, I remember, so I've given you that. So this is the previous diagram now. So you can see there is a formula written here, and let us have a small talk on this. After that, the topic will be over. So the fourth postulate that was given by Bohr, it is the gap of energy. It is equal to hf or hc by lambda. So what is happening here? So hf is equal to the gap in energy. Energy is written as negative 13.6 divided by n square. So for you can write it as n2, and here you can write it as n1, and accordingly you can create this formula for yourself. So 13.6 1 n1 square minus 1 by n2 square, because this negative and negative is going to cancel each other. This becomes the formula if you want to find the frequency of whatever radiation that will be emitted. I told you that ultraviolet will be there, so it is written here. You can see if you are jumping into this Lyman series is giving ultraviolet, Balmer series is giving you visible light. The violet and blue and red and all colors are given. Red, blue, violet. These all are coming from the Balmer series. If you're going for n is equal to 3, you're taking infrared. And similarly, the other variations, they're also infrared. So this is the last part we wanted to do in the case of energy. I know the video has become quite long, and this is a lot of information packed in just one photon. So please try to watch the video a couple of times. Do watch it. There are a couple of things. Okay, don't be confused. Please give me feedback in the comment section. All right, all the best. Bye. Thank you.